All right. Well, it's 9 o'clock. I am going to start with the program that you were supposed to write on Tuesday, because I think about half the class got it, and then the other half did not quite get the program. So I'm going to, just kind of go back to that program. Let me go back to the activity itself. So this way we have a baseline of what we were doing on that particular day. Oh, no, that's not what I want. I want to do a preview. All right, so the first part, which is the lab portion, um, it is basically a step-by-step guide to help you understand the instructions that you need in order to write the program. Um, all right, so I'll just go ahead and answer all these questions, and you guys can let me know if you have anything you want me to address. All right, so the first question is, as an 8-bit number, which bit must be a 1 if a binary number represents a negative value? So that means the VS of the bit pattern has to be negative. So in this case, it is bit 7, because bit 7 is also known as the sign bit. When it is a 1, then the value or the interpretation of the binary pattern is going to have a negative value. So do we have any questions about this one? Nope. Okay, so this one has to do with signed versus unsigned representation. And then the next question is about the second task is to check or to find out whether the sign bit is a 1 or a 0. So out of the 5 flags in the ALU, the sign flag is the S flag, or it is called just S. Okay. I believe we talked about this when we looked into the ALU. So, that answers this question. Do we have any additional questions about um, which bit out of the flags register is the sign flag? Nope. Okay. Then we're moving on. This question here is asking, this one is a little tricky. It was not intended to be tricky. So this one is asking if you are to execute a compare AA instruction, what would be the result in the flags register? So the compare AA instruction is actually hijacked, which means you cannot really run that opcode. If you run that opcode, it doesn't do what it appears to be doing. So what you need to do is to go through the manual process of figuring out what flags will be set and what flags will not be set. So the way we do this is you can do it on a piece of paper. So I'm going to do it on the whiteboard today because it's not going to be that difficult. I'm just going to use 4 bits just so that I don't have to write a whole lot of bits here. So we're going to say x3, x2, x1, x0. And because we are comparing a register with itself, so that means what I'm subtracting would also be x3, x2, x1, and x0. This is the subtraction of compare a register to itself. So it doesn't really matter what the bits are, what are the values of x0 to x3, because when you look at the Q row, they're all going to be zeros. And then when you look at the T row, they're all going to be zeros too, because x0 minus x0 means it is the same thing. So it's either 0 minus 0 or 1 minus 1, and it's not going to give you a borrow. So that means the entire borrow row or T row would be all zeros. And then when you look at the D row, which is the difference, because the Q row are all zeros, and then the T row is also all zeros. So that means the D row is also guaranteed to be all zeros. Now, obviously, the question ask about an 8-bit subtraction, but there's no need to write all 8 bits out because it's going to be the same pattern. So given that is the case, okay, now we have to figure out the 5 bits in the flag register. So we start with the carry flag. The carry flag is really the borrow flag over here. We talked about this when we looked into the ALU. The borrow flag after subtraction is reported as the carry flag when we look at the flags register. So that means the carry flag is going to be a 0. The next one up is the Z flag. So the Z flag is going to be a 1 because all of these are going to a NOR gate before it comes out. Okay. So this is all going through a NOR gate. So when this is all coming out, it's going to be a 1 because the OR of all the zeros will be a 0. But because it's a negated OR gate, so that means that final 0 is also going to be negated to become a 1. So that means the Z flag is going to be a 1. The next one out is the sign flag. Once again, the sign flag is this one here. So that's going to be a 0. The overflow flag after a subtraction is essentially saying this bit over here, which is our the subtrahend, and subtrahend. Yep. So the most significant bit of the subtrahend and the most significant bit of the difference, they need to be the same, but we also need the minuend and the subtrahend to have different most significant bits. So in this case, because they're both the same, so we know the overflow flag is also going to be a 0. And then the L flag is the exclusive OR between the sign and the overflow because they're both zeros. So that means the L flag is also going to be a 0. So the correct answer to this question is 00010. Okay. I think some people, I did not intend this, okay, but some people got tricked by reporting the bit pattern backwards. Okay, but we have always counted bits in the sense of bit 0 is all the way to the right hand side. So I think some people kind of wrote down the bits in the opposite order. So they kind of did not quite get the answer to this one. And then the next one is starting to get a little bit more interesting. It has to do with which bits are hijacked and which one is not. I think we talked about this in the class, okay, which ones were hijacked and which one was not hijacked. So the one that is, okay, I have to read the question of which one I'm asking. Okay, TAC remembers that some operand combination opcodes of either the AND or the OR family are hijacked, but I cannot remember which one. Analyze the opcode table and find out which family is hijacked. So the one that is hijacked is the OR XX family. And the way we know that is the family that is hijacked is when you go to the opcode table, you look up the OR instruction, it is 1101, and then we have the 4-bit patterns over here. So when you look at the other opcode over here, which is increment x, you can see how both of these start with 1101. And then they both have x, one has XXYY, the other one has XXXX. So that means when you say OR AA, it really is the same thing as increment A. So increment A as in mnemonic is actually hijacking opcodes from OR AA. So that's the reason why in this case, the answer is OR AA, which leaves AND AA the one that is not hijacked. Okay, that piece of information is going to be useful later. So in question number 5, it says, combining the results of the previous steps, now we have an efficient way to check whether register X has a negative value or not, because the test XX here, this is going to be AND XX. And then the question is asking what is JYI. So JYI in this case should be JSI because we are checking the sign bit after the AND AA operation. So that's why this one is JSI. Are we still doing okay so far with this? Okay. And I believe we're getting pretty close to the last question, or this is second to the last. This one is asking, so it's giving you a template of code already, okay, with the italic, indicating things that you probably need to change a little bit and not use exactly what is in the um, comments over here or in the code template over here. So this one is asking which one is going to give you a negative value. The one that is going to give you a negative value would be 155 because the bit pattern of unsigned 155 is actually also representing a negative value. I believe it is negative 101. Is that okay? All right. All right, so now we move on to the last question of the quiz portion. So at this point, you might want to write some code, assemble it, and test it in the simulator to make sure that the sequence of mnemonic from the previous step does work as expected. And guess what? I know many people did not do this step. How do I know? Because many of the submissions did not even assemble. Now, if you ask me, was I, disappointed? The answer is no. There's no reason for me to be disappointed. I am not your parents. I'm not you either. So I'm not in a position to be disappointed. However, I really think that people should be following the instructions a little bit better to kind of make sure that things are working up to a certain point before proceeding so that you don't lose the point. Okay. So anyway, that's important. Okay. Reading the instructions and following the instructions is important. Now we are ready for the next step of this program. How do we perform arithmetic negation? Specifically, what is the name of the following C or C++ expression with respect to the bit pattern X? Now this one is multiple choice, which means you really can just kind of check out which one makes sense and which one does not make sense. This is not logical negation because logical negation is a single exclamation point. This is two's complement, but we can rule out the other ones too. Bitwise negation is just tilde x by itself. One's complement is also the same as bitwise negation, which is just tilde x by itself. So the only two contending options is either none of the other choices is correct or it is two's complement. So two's complement is important because that is also what you need to do in the actual program so that you can perform the arithmetic negation of the value. So all of these steps are designed to help you step by step to get the program done so that by the time you get to the spacer, it is just going like, okay, go to the code upload assignment, and it has instructions over there too. So now we're going to go to the code submission interface and work with that. So we go back to, okay, first of all, let me just submit to make sure that I get a perfect score. Okay. And yep, good, 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 good. All right, so I think I am getting a perfect score for this one, 7 out of 7. All right, so at this point, we can now continue with the actual code itself. Okay, so we're going to go back to look at the code submission interface because that has its own instructions. Okay, so this one also gives you kind of like a template, which is the same template as last time. So what you need to do is to work with this template over here, and there's instruction also to tell you that you have to insert the assembly code to perform this somewhere. So you have to find out where that needs to go. So let me go to this interface and actually type the whole program in. This way we can test it a little bit. Okay. So even if you're not using Reefer Spider, which is a really handy tool to kind of test run the code, you can still run this code inside Logisim, and it will still give you sufficient information to proceed with the coding here. So no up, and then I define the next one, which is labeled K1. We can give it, like the actual negative value. LDI K1. So instead of test, we know this is AND AA, and then we have JSI, sorry, to label L1. And then after that, we have a halt instruction at label L1. We have another halt instruction. So there we go. The instruction here is already, the comments is already telling you something about the program. If A is less than 0, which means the sign flag is a 1, go to label L1. So that means label L1 is indicating, if you get to label L1, is telling you that A has a negative value, which is where you need the arithmetic negation code. Okay? And I saw a bunch of people putting the arithmetic negation code to the wrong branch. Okay, so that means those people did not read the comments that are included in the template of the code. Okay, so either they did not read or they did not understand. Either way, I am a little bit concerned. All right, so now we look at this code and go like, okay, but Jack, are we really sure this code is working? Well, let's just say that we don't know. What are you going to do? Test it, exactly. So how do we test this? Okay, so we'll go ahead and test this code. So we'll go ahead and put this into the actual assembler. Okay, so we go to the assembler, and you can sign in to, kind of take a look at the assembler right now, just in case you want to take a snapshot at some point in time. So we're gonna take out the code already here, and then I can just type the whole thing in, or I can just copy and paste it. I will do the shortcut thing. Okay, so I can, in VI or Vim, you can actually specify the entire code. Okay, 1 to 8. You can pipe it to the clipboard, which is really handy, and then I can paste it over here. All right, so I'm just the program is now assembled because I don't see any errors here. So we go to the RAM file, and then we download this RAM file. Okay, so we go here, we go to save it as CSV, and we'll just call that abs.csv because the program is ABS. So now we have to start up Logisim. So let me go ahead and start up Logisim from here. All right, so here's Logisim. We have to load the processor file. There we go. And then go to the RAM component and then load the image that we have just created, which is called abs.csv. Now the program is here. So all I need to do is to run this thing at full speed. Okay, this is already enough to tell me whether the program is working or not. So we go to simulate, take frequency all the way to the highest possible one, and then type Control K to start the program, and the program is now done. So you go like, but how can we possibly tell whether the program is working or not? The answer is, where is the program counter when it's all done? When the program count, in this case, the program counter is 08, but this is after it increments, which means the instruction or the location is corresponding to 07. So then we go back to, I just got past that point. There we go. So we get back to the assemble view of the assembler, and we check out what is at location 07. It is the second halt instruction. So now we go back to the template of the code, and then we ask, are we supposed to get to the second halt instruction if register A has something that is negative? What do you think? The JSI says branch if and only if the sign flag is a 1. If the sign flag is a 1, it means the value of register A is a negative value. So we are at the correct halt instruction. Okay. Then you go like, well, but heck, maybe the program is going to go to label L1 regardless. We got the wrong branch instruction. Well, that's possible, right? So then what do? We change K1. We change K1 to something that is non-negative. 4 is fine. So the easiest way to do it is to go here and then just change that particular byte um, to a 04. So we can actually go to edit content. I will move the window into view. You don't have to do it this way. You can just change the code, reassemble, and then just put the whole thing back here. I'm just too lazy to do that. So I just look at these instructions and I try to find out which of these bytes is the 155. So there are two ways to do this. The quickest way is to use the assembler to help you. So there we go. So when you use the assembler to help you, right here is the assembler. So we can see that the K1 is this byte over here, which is at location 02. So now we switch back to Logisim, go to location 02. This is 0001. This is 02. And we just kind of change that one to a 04, and then we close the window, go back to Logisim, and now the program is now changed to only use 4 as the result. And then we basically, make sure the clock is low, click the reset button over here to reset the processor so we can start from scratch again, and then type Control K to go through the simulation. and control K again to stop it. So this time the program counter is 07, but remember this is after the increment of the fetch operation. So that means the program counter or the location of the instruction that we are stuck at is actually at location 06. So if you go back to the assembler and you ask what is at location 06, it would be the first halt instruction. So the program does differentiate between what is negative and what is not negative. If it is negative, it goes to the second halt instruction, which is after the L1 label. Otherwise, it just falls through with the JSI instruction to get to the first halt instruction. So do we have any questions about this analysis of the code? Nope. Okay. So that means this code is working, okay? It can differentiate whether register A has a negative value or not. So now the only thing I need to do, going back to here, is to add the code to perform the two's complement. The two's complement code is already given to you in C++ syntax. In other words, when you look at this portion over here, I'm already telling you what we need to do. Okay, we have to negate A first using a bitwise not, and then add one to the result after the bitwise not. Okay, so the ordering of that operation is also specified here. So the only thing left to do is to look up the opcode table, particularly pay attention to column C to find out how we can do that. The arithmetic, not arithmetic, but the bitwise not is done by this instruction, which is not x. The increment is done by plus plus x, which is the increment x instruction. So now we go back to the code here, and then we just have to say, okay, do a bitwise not with register A, and then increment the value of register A. So now we have the whole program done. Okay. Um, what I saw when I graded this particular submission was many people did not even bother to put this code into the assembler to catch like syntax problems and instruction issues and whatnot. Um, yeah, so don't do that. Okay, always spend a little time to double check before you turn it in. Okay, because from here on, if the program does not assemble, I'm not going to give any points. Okay, because it just does not seem like it's worth any points if it does not even assemble. Now, if it assembles, the instructions are just at the wrong place or something is wrong, that's a whole different thing. But if it does not even assemble, I don't know what kind of points I'm supposed to give to those programs. All right. So I hope I'm making that part clear. Yep. Okay. All right. So um, are we okay with this program? We good? All right. Excellent. So what we're doing today is to work on function calls now. Okay. Today's lab is called compiling C control structures. So that is the lab for today. Which is down here. This is the lab for compiling C control structures. You can't see it yet, but I will release it in time. So that's based on the material that we talked about on Tuesday. What we'll talk about today is how do we call and return in from a function perspective. So what we are doing today, I'm just looking at the notes here. Calling and returning from subroutines or functions is the actual topic for today's class. So this is really kind of important. It's orthogonal in a way compared to the previous topic because we are not dealing with control structure. We are only trying to look into how do we call a function and how does a function return back to the caller. That is the focus of this particular module. And it starts with a simple program that we go like, okay, this is not a very useful program. Main is going to call f, f is going to return to main is going to call f again, and f is going to return to main again, at which point we are done. Okay, so you can actually put this program into online GDB or any type of C++ environment and watch it run. But I'm hoping that we all understand the behavior of this program, at least from the perspective of C++. Are we okay with that assumption? Okay, so nobody has a question about the behavior of this program, how the first call of F returns to the second call of F, and then the second call of F is going to return to the return zero of main. So are we all good with that? Okay, excellent. So now the question is, how do we do this in assembly language? Okay, so what we'll do is we are going to construct a program kind of step by step, but before we do that, we also have to understand the concept of a stack. So a stack is a last in, first out container. Okay, that's the best way to put it. It's a container of something, of some kind. You can put things into it, and then you can get things out of it. All right. So there are two types of operations as far as we are concerned at this point. One is to put something into the stack. The other one is to say, okay, I want to retrieve something from the stack. But you cannot just retrieve anything from the stack like a regular array. You can only retrieve things from the stack based on the order of how you put things into the stack to begin with. Is that okay? So the best way, or one of the more graphical way to understand this, is to think of a real stack of paper. Okay, just think about you have some post-its or some a little stack of card, those little, how do you call those little cards for studying? Flashcards. Yep. So just imagine they have some flashcards, which we may have some over here, but I don't even need that. Okay. So imagine that you have a stack of cards, okay, but most of you cannot really see the ordering anyway, so I'm gonna just draw some pictures. So you have a stack of cards. The first one that you put onto the table, let's say it has 25 on it, okay, and then you put another piece of card on top of that, which let's say has a value of 42, and then on top of that you have another card that has a value of 61, okay. So when you remove the cards, okay, the restriction is you can only remove the card on the top of the stack. So that means if this is the order of putting in the cards, so the order of putting in is 25, 42, and 61, then these are what we call push operations. Whenever you want to put something into the stack, it is called a push operation. So if I need to retrieve something, it is called a pop operation. Okay. So what is the first card, or what is the value on the first card that I'm retrieving from the stack? 61. That is correct. So the pop is going to get rid of the 61 first, at which point this card is now gone. So if I push again, okay, if I say, okay, I want to stack another piece of card here, I want to push, let's say, 12 over here, okay? And then I go and for another pop operation, so I have another push of 12. And then if I do another pop, what value am I going to retrieve? 12. That is correct. If I pop one more time, what value am I going to retrieve? So once you pop, the 12 is gone. 42. Very good. And if I pop one more time, what do I get? It'll be the 25. That is correct. All right, so I think you guys are understanding at least, abstract sense, what is the stack, okay? Last in, first out. All right, which is a very odd kind of, way of, putting things in and getting things out. In real life, most of the time, we don't want last in, first out when things are actually last in, first out, okay? One example is the refrigerator at home. Okay, you don't really want the refrigerator to be last in first out because that means all the stuff that you bought like a few weeks ago that you haven't finished is sitting in the back of the refrigerator, and the stuff that you just bought today is at the front. Okay, which also means the back of each shelf becomes a little mold garden, with colorful green, purple-ish, kind of mold growing on your bread, your potatoes, your salad, and whatnot. Okay, so that's an unintentional stack. Okay, unintentional LIFO when we really want it to be FIFO, first in, first out. Okay, all right. So what we also want to do now that we understand what is push and what is pop, and this is just another example, a huge example of the ordering of pushing and popping and what would be the content on the stack. So it's just a non-graphical way to illustrate essentially the same thing. So what we want to do is to say, okay, how do we implement something like this? The code is already written here, but what I'll do is not really just to read the code, and instead we're going to use online GDB and actually have some fun with it. So we're going to go to online GDB and then write some code over here. So this is this is a regular C program will work in this case. So I'm just going to take out this. And instead, I will define a few things. Okay, define stack size to be 32. It's just a macro, which means every time the compiler sees the word stack size, it would just replace it with 32. So here we do a uint 8 underscore t stack, and then we have stack size in it, which also means I need to pound include standard integer dot h, like so. So standard integer.h is a header file that defines the type defs or type definitions that allow me to specify something like uint 8 underscore t. So uint 8 underscore t, this particular type here, is basically saying we have 8-bit unsigned integers. Okay, that's basically what it means. And so stack, which is nothing more than just an array of 32 of these things. Yep, it's just part of the name. Yep. So anything that is a type def, has the underscore t to help differentiate it from other things. Yep. Mhm. All right. So that's one. Okay, another definition that we also need is a stack pointer. So a stack pointer is going to have the same type, okay, except it is a pointer to that type. So in this case, a stack pointer is a pointer to an unsigned 8-bit integer. All right. And the way we initialize the stack pointer is kind of weird, okay, because we say the stack pointer is the address of one element past the end of the entire array. So this is not the last element of the array. This is one past the end because we count from 0 because everything the indexes start from 0. So that means the index of the last element of stack should be stack size -1 or 31 to be exact in this case. So why are we doing this? I mean, this means SP starts with an address that is not even an element of the stack. Okay, so that's I will address that question later. And now we're going to define a few more macros. So I'm going to define the push operation. So push X is a macro that is parameterized. What that means is the C compiler would expand push and whatever into whatever the definition is specifying next. So I will give you the definition right now. So what it will expand it to is SP minus minus SP equals to X. So that's an expansion. Um, Essentially, what the compiler does is if I say push 31, it is going to say, oh, okay, I'm just going to textually, using text or lexically expand push 31 to asterisk, open paren, minus minus SP, close paren, equals to, in parentheses, 31. That's all it's going to do. Okay. So it's really just a shorthand, so I don't have to redo, that thing over and over again. So we're going to get rid of hello world because, that's just not useful. So we're going to say push, okay? We're going to use the same thing on the whiteboard, push 25, and then we have push 41, and then we have push, 61, okay? All right, so now we also need to define pop. So the pop operation is going to look like this, okay? So pop is going to look like, I just want to use a printf, which is kind of the way that you print a value out in C and not in C++. It is the same kind of thing as C out, okay, in C++, but because I personally prefer to use C when I don't need to use the object-oriented programming paradigm, so I just use the regular C here. You don't really have to know what this is doing. Okay, this is print formatted. That's what the F stands for. Okay, and then I need a typecast. Okay, because otherwise, the unsigned AB integer is not going to match what this should be expecting. And now we can specify asterisk um, SP plus plus. So it's a post increment, SP. There we go. There you go. Okay. So now we, kind of replicate, what we see on the whiteboard. We have a pop operation. Oh, okay. We just want exactly pop. There we go. And then we have another push 12. And then we have another pop, and another pop. All right. So what we are seeing in the program is something that is resembling what we see on the whiteboard. Okay, so that means we should be seeing the program should be printing 61, 12, 42, and then finally 25. So before we actually test run this program, I want to make sure that we all understand the concept of pushing and popping. In other words, everything on the whiteboard is understood. So are we comfortable with what we are seeing on the whiteboard, the abstract concept of pushing and popping on the stack? So we all good with that? Okay. So now we can try to run this program and see whether it will give us exactly the same sequence. So we'll go to, we can just go ahead and run it because it prints something to the standard output. So here we go. So we will take a look at the output and see whether it is the same sequence. So it says 61, 12, 42, and 25. So they all match up, okay? So now we can go back and try to take a look at the code here and go like, okay, what exactly is going on with the push operation and what is going on with the pop operation? So the push operation, which is consisting of this particular portion here, which you can hardly read. Um, I can go back to the notes here, okay, because it's the same thing. So what we see on these two lines is the same thing as the push operation, except it is spelled out on two separate lines instead of using a pre-decrement. Is that okay? So the first thing we do is we decrement the stack pointer. Remember, the stack pointer was initialized to point to one location past the end of the array stack. So by decrementing the stack pointer first, now it points to the very last element of the array, which is good, okay? Because now the address that the stack pointer is pointing to after the auto decrement is now the address of the last element of the array. And then all we do is go like, okay, what value do you want me to save at that location? That's just whatever x turns out to be. And we overwrite the location that the stack point is pointing to. That's why we have a dereference here. That is how we push. The first operation, which is the decrement of the stack pointer, is quote unquote the allocation of the space. And then the second operation is to overwrite the space that we just allocated. So that order is important. You allocate first, and then you overwrite the location that you just allocated. You don't do it the other way around. Okay. So the pop operation, as you can see down here, is the exact opposite of the other one. So in this case, we are retrieving the value to a particular variable x. We don't really know exactly what that is. In an actual assembly language program, this X here is one of the registers. Okay, you want to pop a value into a register so we can use it for whatever purpose we need to use it for. But the operation is still the same. Okay, you can see how um, the last operation of a push becomes the opposite of the first operation when we pop in every way possible. Okay, you can see that the the assignment is flipped over here. What is the second is now the first. Are we good? So that means, whatever the stack pointer points to is the first value that we need to retrieve, which also means the stack pointer always points to the top of the stack. All right. So once we retrieve the value, what do? We go like, oh, we don't need that anymore. We remove that piece of paper off of the stack. And the way to do it is to do a SP++, so that the stack pointer points back to the previous item that we push on the stack. Okay, so the one thing that is confusing is the stack pointer is growing down. The more things we push on the stack, the lower the location the stack pointer is going to point to. So that part can be a little bit confusing because that's not how we see it when we actually look at the stack of paper. Because when we stack things up due to gravity, the top of the stack is actually up, but when we push things on the stack from a memory perspective, it is pushing down. So are we still doing okay so far with this? We good? All right. So now that we have the concept of a stack, we can now go back to the C code here, and then we try to answer the question of, okay, how do we implement something like this in assembly? So this is the second part of this particular discussion. So I'm going to write a program called, we'll just call that call return, okay? Call return.ttp-asm. And in this program, the first thing I would do is I'm just going to copy and paste the entire C code into the assembly code, like so. And obviously, it is not syntactically, correct because we are looking at the wrong syntax here. So I'm going to replace all the beginning lines with comments. Uh, Substitute, oh, beginning of a line, slash slash with, oh, no, the beginning with slash slash. There we go. Okay, there we go. So I have just commented out all the C code. The beginning of a function is indicated by just a label of the same name. So this is how we can indicate the entry point of each function when we implement functions in assembly. So that part is not too hard. Okay, it kind of makes sense, right? Because if we need to call function f, that means at some point we need a JMPI to the label f. So why not use the same name as the original C function? So that kind of makes sense. The end of main, at this point of time, we're just going to say we'll put a halt instruction here instead of a return zero, okay? But later on, we can actually do a return zero. But right now, I don't want to complicate things. So that part is kind of easy. So for the function call to f, we know that at some point, we're going to have a JMPI to f. And also the same thing over here. At some point, we have a JMPI to f. So when you write this code, you probably want to leave a lot of room because I'm not writing this code sequentially. So I'll be inserting a lot of things in between. But you can also, when you write node, you can also use a pointer go like this goes into this, go between this, because I want to explain the rationale behind the whole thing. So now you look at this and go like, okay, um, how does the function f return to the right spot? That becomes the problem. Going to the function, calling the function is not the problem. Returning from the function to where it's supposed to go back to is a problem. So, in the function f here, okay, when it is all done, we need some kind of a branch to go back to the right place at the caller. That becomes a problem because the JMPI instruction will always go back to the same spot. It cannot go like, well, sometimes we want to continue execution at line 12, and other times we want to continue execution on line 14. Can't do that with a JMPI because the I stands for immediate, which is a constant. Okay, so you go like, okay, that's a problem. But even the bigger problem is how can we even tell the callee function f in this case where it is supposed to go back to. We have to save the return address. Okay, we have to save the return address. So let this so let's take a look at this. Okay, after this conditional branch to f, where would where do we want the function to return to? Well, I suppose we can use a label here, right? So we can say this is the return address 1, which is the return address after the first call to f. It's just a label, okay? The name return address 1 has no special meaning other than self-documenting as a label, okay? But it marks the spot of where function f should return to once it's done. Does that make sense? Okay. So for the same reason, we can now go to the second one and go like, hey, second call to function f, when you're done, go back here. Okay, it's a different label, but it serves the same purpose. Is that okay? So now we need to somehow let function f know where it's supposed to return to. You go like, okay, we have a whole bunch of scattered concepts now. Okay, we have the original C code, where we call f twice to illustrate that it needs to return to a different place. Okay, that's one piece. And then we somehow kind of digress to talk about the stack, which seems to be disconnected from everything else. And now we are looking at the assembly code and go like, we have a problem that we don't know how to solve. So there are three pieces of things that we have talked about, but they are related. So that means the stack has to be somehow be involved here. Is that okay? So the way the stack is involved here is before we jump to F, we have to first push the return address. So this is the first one. So we have to push return address 1 here. And this is the second one, which means we have to push return address 2. Okay. Well, if you push something on the stack, somebody is probably expected to pop that piece of information, right? So who do you think needs to pop the return address? The the end of function f. Very good. Okay. So at the end of function f, that's when we need to make use of the return address that was pushed earlier. So that means I'm going to put it about here. So that means at this point, we're going to have to pop the return address, okay? And we'll pop it into some register, okay? You pop to register, we'll just use register C for this, at this point. And then what do we need to do? What do you think the program needs to do at this point? Now that we have the return address already popped into register C, what would be the next thing that we need to do in order to continue execution at the right place? A jump is good, okay? But what we really want to do is we want the program counter to be the same as register C. Is that okay? Because the program counter is a pointer to where we are going to fetch the next opcode. So if we change the program counter to return address 1, that means we are continuing execution at return address 1. If we change the program counter to return address 2, that means we are going to continue execution at return address 2. So PC equals C is what we want to do. Okay, but I have not introduced that particular opcode or mnemonic yet in this class, so we're going to go find it together. So we go to the opcode table, focusing on column C, and then we ask, okay, how can we copy the content of a register, A, B, C, or D, into the program counter? I think the mouse pointer is accidentally at pretty much the right spot. So what is the name of that instruction? What is the mnemonic? JMP without the I, and then you specify a register. Is that okay? So, okay, that is kind of cool. I think we have almost all the pieces. Okay, so if we go back to this here, we kind of like, oh, okay, this can be done with JMPC. Okay, cool. All right, almost everything is in place except um, where's the stack pointer? Have we talked about a stack pointer up to this point in when we talked about all the registers inside the processor? I don't think so. Let's see. We have eight registers A, B, C, D inside the register bank. We have the program counter. We have the instruction register, and then we have the flags register, and then we also have the microcode pointer. Those are all the registers that we have talked about. There's no stack pointer. So what do? We just look at the four registers in the register bank and say, register D, you're it. We just designate one of the four registers as quote unquote the stack pointer. We don't want to put it in RAM because the stack pointer is used a lot. Okay, you really want it to be in a register. Yep, yep. Go ahead. It could have been any one of the four registers. I just chose register D. Yep. So it is a convention. It is not something that is limited by hardware. The hardware says all four registers are the same. Okay. Whatever you can do to register A, you can also do it to register B, C, or D. It is just a convention. It's just tech saying I'm going to use register D as my stack pointer. Is that okay? So it's not a hardware thing. It is just a convention thing. Okay. All right. Well, that might be helpful. Okay. Because that means whatever we need to do here would be something. See, originally it would have been something that looks like this. Okay, pre-decrement p, and then we want to store return address one over here, and then over here it is kind of the same deal. Okay, except it's a different value, right? And then over here when we pop, it is kind of we can now say okay, it's the same thing as register c is going to be sp plus plus, right? That's coming from the C program. Okay, the way we use the stack pointer as a variable in the C program, I'm just replicating all that code over here. But then we go like, but tech, you just said that there's no actual stack pointer. Stack pointer is really just register D. So that means, oh, okay, we can do that. So replace everything that says SP with D. Okay, like so. Are we good so far? Are we still following? Are you guys still following the progression of the concept? Okay, all right. So if you're writing it down, it's okay to cross out SP and just put a D over there because that actually helps to emphasize that, oh, there's no designated stack pointer. We are just using the register D as a stack pointer. Okay, okay, all right. So now what do? Well, we look at all of these things that we need to do, and then we try to figure out, do we have all the instructions that we need to get this done? So we can try a few things. So don't write this down because none of this is going to work. Okay. So I'll give it a try and go like, okay. So this is the same thing because it's a pre-decrement. So it's the same thing as decrementing first, and then we do the dereference. And same thing over here. It's the same thing as decrementing first before we do the dereference, and then over here it is the same thing as doing this, and then we do the post increment. Okay, are we doing okay so far? That's a C++ kind of thing. The professor of CISP 360 should have taught this concept already. Okay, pre-increment means doing it before the expression. Post increment means do it after the expression. So are we good so far? All right. So we look at this and go like, oh, this one we know how to do. It is just incrementing D. So it is just, increment D over here. Cool. This one is just decrement D. We know how to do that. And then this one here is just decrement D. We also know how to do that. Cool. Not a problem. That's the easy part. The difficult part is this one here, okay? How do we get the label, get the value of the label return address one, and then store that value to whatever D is pointing to? You go like, okay, let's look up the opcode table and see if we can get a clue of how to do that. So when you look up the opcode table, you see that this is the only time when the left-hand side of an assignment is dereferenced. So that means we have to involve the ST instruction in some way. Is that okay? You don't have a choice. This is the only way for you to store to a memory location that is pointed to by a register. You don't have a choice. So we go like, okay, fine. That means we have to do a std something. And since we're trying to store return address one, we'll put it over here. And the syntax checker does not like it. And then we can try the same thing over here. Okay, the syntax checker is also not going to like it. std return address 2. It doesn't like it. Why? Look at the description of column C. What is X here? It doesn't say I, it says X. What is the difference? X has to be a register. That's right. Okay. X has to be a register. Is return address 1 a register? Nope. It is an expression. You go like, darn it, can't do it that way. Okay. But can we put return address 1 into a register first and then we use the ST instruction? Yeah, we can do that. Okay. So that means I can now use LDI. Okay. LDI is the only one you can use in this case. So we can use LDI stash return address 1 into register A in this case. And then we just go like, okay, that value is now in register A. So everything is good now. And you don't have to use register A. You can use register B if you want to. So now we could do a LDI register B with return address 2, and then you remove that label, change it to a B. So everything looks good. Is that okay? So we're almost done. Okay, we go back to the function that we're implementing. The increment D is already doing the second part of popping. So we just need something for the first part. This one is easy. Okay, C is getting whatever D is pointing to. Look it up and find out what we can do with the instruction set. So I'm gonna scroll up so that we can see that part. So which instruction should be used when we want to use one register to point to the location and then retrieve the content at that location and store it to another register? Hmm? LD. Yep. The LD instruction. That's all we need. All right. So we get back here and then we do LD, C, in this case, D over here. And that's all we need. And then we just need a JMPC instruction here, okay, as we discussed a little bit earlier. And that's it. That's what this program is not quite done, okay? It still has a few little things that I have to take care of, but for the most part, it is done, okay? Are we understanding the concepts? Do we have any questions about the program as it is now so that I can address those questions first? Are we all good? All right, okay. I'm just double checking and make sure the recorder is still on. If it's not on, it is still actually okay because we went through the same lecture on Wednesday, yesterday. So it's kind of the same thing. All right. So if this is almost all done, the question is, so which part is not done? Well, as it turns out, because the program always start execution from location 0, 0, so that means the first thing it's going to do is function F. That's not how we want it to do it, right? So we have to do a JMPI to main to make sure that main is still serving as the entry point of the entire program. Is that okay? And then also on top of that, if we want to use the tool that I've been talking about, which is Refer Spider, we need a no op instruction at the very beginning of the entire program. Just because of a bug in Logisim, we have to do it this way. So now the program is pretty much ready to go. So do you guys want me to run this code and then look at the trace, or do you want to kind of look at this code a little bit more and see if you have questions about the code? hmm So the label, when you look at line 24, for instance, what happens is the assembler would notice that this is a label definition because it's an ID followed by a colon. So it will first identify this as a label definition. And because the label definition doesn't come with anything after that, so it becomes the definition of the label is going to be the address of the assembler at that point. So from your perspective, it will be the address of the decrement D on line 28 because that's immediately at the location of the label itself. So that's what the assembler would do is it would notice this is a label definition. It doesn't have have an expression next to it, so it would just go like, oh, okay, without an expression, I'm just going to assume that I am marking the current address in the assembling process. Mhm. And to make it more visual, okay, uh, any other questions before we move on? Because I want to make sure that we look at this code and we go like, yeah, I think we have a pretty good idea of what each instruction is doing, but I want you guys to have that confidence first before we try to run the code. Are we doing okay so far? Okay, see some nods. Okay, all right. So we'll go ahead and try to get this program into the assembler first because I want to show you a few things in the assemble view of this particular code. So I'm going to do the same thing, one to the last line, right to the pipe of xclip cell clip, and then I go back to the assembler, go to the source tab, get rid of the existing code, and then put the new code in, like so, and then just wait for it to finish assembling. It's going to report error and whatnot, but it should go away soon. Double check everything is good. Okay, so as promised, we are going to take a look at the assemble view first. And particularly, we want to take a look at return address to as a label definition. And because return address to is here, the actual definition is going to be the 1, 2 of column W. And then likewise, when you look at return address 1, which is defined here, the actual value of return address 1 is 0C over here. Now, can you be sure? Because well, you can be sure because you can go to the sim tab table. It's a little bit harder for humans to read, but you can always, quote unquote, pretty print the JSON representation. But even if you don't, you can look at return address one. It is defined on line 23 and it has a value of 12. So that is how you can confirm how a label is defined. Return address 2, on the other hand, is defined on line 32, and it has a value of 18, which is 1, 2 in hexadecimal. Are we doing okay so far with kind of learning how to read the JSON representation of the symbol table? Okay, that's okay. It's all right. This is under the hood of the whole assembler. hmm Any other questions before we proceed? No other questions? All right. So we are going to run this program from River Spider, because this will show us the actual flow of the program, and not only that, it will also show us all the stack related operations. So that's why this tool is, I think it is really useful because I made this tool as an instructional tool. I really did not need the tool myself, but I think from your perspective, this tool is helpful. So we'll take a look at the trace. The trace is always in the analysis tab. So go to the analysis tab. So now I'm going to describe, how you can read this portion here. And for those of you who want to have a copy of your own, and so that you can annotate this whole thing, or you can print it out on a piece of paper and then just put stickies on it and whatnot, now would be a good time, okay? Because now is a good time to take a snapshot of this thing, go to File, and then go to Make Copy, okay? And then you can make your own copy at this point. So you just go to here, go to Make a Copy, then you have a snapshot of the assembler right now at this point. So that can be handy, but I'm gonna stay like this here for a while, okay? So you still have some time. So the way this works is column A is the program counter. Okay, when the program counter is 00, it corresponds to line 1 of the source code, which has a the line itself is a no op instruction. Okay, so that's how we read the 3 columns. Then it moves on to um, location 01. At that location, it corresponds to line 2 of the program, and the actual instruction on that line is JMPI main. And that's why it skipped over a bunch of bytes going to location 06 because main starts at location 06 in RAM. And then the first thing it's going to do is a decrement D. And decrement D is going to change register D from 00 to FF. Okay, so when you look at this particular cell, the choice of using a single equal instead of a double equal was intentional. In other words, this is representing the change of register D to FF. It is not saying that register D is FF to begin with. This is a change to FF. The single equal symbol is assignment. It has the same meaning as in CISP 360. And then what do? We move on to location 07. Location 07 is corresponding to line 21 of the program, and it has this particular code on that line, which is LDI register A with the label of return address 1. The result of this is register A is getting the value of 0C, which is 12 in decimal. Is that okay? So once again, A equals to 0C in hexadecimal means we are changing register A to 00001100 in binary. Are we good so far? Are we kind of getting the how to read the trace? Okay. And then we have the next line, which is actually significant. This is how we actually push the item. So at location 09 of RAM, it is corresponding to line 22 of the program, and it has an instruction of store indirect D with A. The result of this is indicated here. So once again, the single equal means assignment. The asterisk means dereference. So this means the action being performed here is to store the value of 0C in hexadecimal to the location FF in RAM. Are we doing okay so far with understanding the cell that is highlighted at this point? Okay. So what that means, okay, if I were you, I would look at this entire block of code and say, oh, we are pushing return address 1 with this chunk of code here. And I would include the next row too. Okay, there we go. So I would look at this and go like, okay, this is how we push the return address of return address 1 on the stack. Is that okay? Now, if you take a snapshot of this, you can do anything you want. Okay, you can now go to the color thing and go like, this is a chunk of code that I want to highlight together. You can even go to the border tool. Okay, you can go to the border tool, which is right here, and go like, I want to put a border around this whole thing because it is important to me. Okay, so these are the things that you can do once you have a snapshot or a copy of the current assembler file, which I think is helpful. Okay, so I'm not gonna keep with those things. In fact, I'm gonna have to delete the note here, okay, because that's from the previous class. So I'm gonna remove the notes here. So delete notes. So you have a variety of ways to annotate a trace to help you understand how things work when we are getting to this point. Are we okay with that? Okay, because I don't want anyone to tell me I have no idea what the code is doing. You never taught us how to do this. Well, I'm trying my best to do it. All right. So after we push the return address, what do? We get to location 09. Oh, I take it back. We get to location 0A, and all it's doing is a JMPI to the label F, which means we are now continuing execution at label F, which is the entry point of the function F over here. So that's why the next location is 03 because that's the entry point of function F. Function F doesn't have anything to do, so it's starting to return right away, which means I'm retrieving the return address from the stack. Okay, this is the first step of a pop operation. So when you want to look at the entire pop operation, it would go from here to over here. This entire block is the pop operation. The first thing it does is to use register D, which is currently FF, go to that location in RAM, figure out what is at that location, which is 0C, retrieve that 0C, and then put it into register C because we are popping into register C. That's the first operation. The second operation is a post increment of the stack pointer. So the stack pointer increments from FF to 00 as a result of the increment. Are we doing okay so far with this? All right. So the important part is two things. The stack pointer is now back to where it used to be, and then register C contains the location of where we need the program to go back to. So when we get to location 05, which is the JMPC instruction, then it just goes like, oh, okay, since register C has 0C in it, the program counter will now be changed to 0C. So that's why the next location that we execute is exactly at location 0C, and therefore we're done with the return operation. So the important part here is we have to do a pop operation starting on this cell, and then the actual JMPC instruction is finishing the return operation. So this entire block here, which includes 3 instructions, is how we return from a function. Are we doing okay so far? Okay, you have to pop the return address and then use the return address so that you can change the program counter to the return address. Is that okay? All right. So what do we do when we get back to main? The same thing again. Okay. So we use this instruction all the way up to here. This is pushing return address to on the stack. So that means at this point, I think it's fairly clear that the stack is a way for the caller and the callee to communicate. We do not use registers for that communication. We use the stack for that communication. The reason is relatively simple. You only have 4 registers. So what if you have more things to communicate than all the registers can do? You run out of stuff. The stack, on the other hand, it can be relatively large, even on this processor. Okay, so it can push a whole bunch of stuff, and then from the caller, and then the callee would go like, "Yep, I know where to find that stuff." Okay, they're all on the stack somewhere. Okay, so that's why the stack is a very essential piece of concept that facilitates a lot of the things that we need to do when you are calling a function and also when you're returning from a function. So after we push return address to, then we get to function f again, okay, the JMPI. So when you look at the call itself will start from here and it ends with the JMPF instruction. This is the call, okay? If you do not include the JMPF, then it is just the push of the return address. If you include the JMPI to the function, then it is the entire call. So once we get to the function, it has nothing to do. It immediately does the return. So the return is also 3 instructions long. This is how we do it in a return. So after a return, the second time it gets to the halt instruction because there's nothing else in this particular program in main. Are we doing okay so far? Are there any particular role in the trace that you want me to explain any further? I'm not seeing any questions here. All right. So, for those of you who think, okay, I need to do something kind of hands-on to really make sure I understand all of this stuff here, let me give you a program so you can kind of chew on it a little bit and try to implement it. Okay, so we'll go ahead and get rid of this program. Okay, this one is just a test program to illustrate, how to use the stack, what is a push, what is a pop. Okay, so we're gonna get rid of this program, and instead I'm gonna have function f over here, which still doesn't do a single thing, and then we're gonna have a function g over here. This is void g, and function g is going to call function f, and then we have the usual main, and inside main we just call function g, and then it has a return 0. So the behavior of this program is relatively simple. Main is going to call g, g is going to call f returns back to g, g returns back to main, done. None of the function does anything, right? But the question is, can you turn this program into the assembly language form using what we have learned today? So that would be a good exercise over the weekend, so that if you do this over the weekend, then by next Tuesday, you will have some really good understanding of how to call and how to return, and then we can stack on top of that, some additional concepts. So at this point, the other question is, how are we supposed to study for this stuff? So the way we study this stuff is called the caller-callee agreement. So this is a relatively long, document that talks about, how the caller and the callee communicate with each other, particularly using the stack. So it goes through basically the same instruction or the same concept that we have just talked about today, which is really just the push and the pop here. But then it will also talk about what is the mutual agreement between the caller and the callee. There are concepts that we haven't talked about. We haven't talked about arguments. You can skip that portion. We haven't really talked about, well, we have talked about the return address, so you cannot skip over this portion. So on the stack, you can basically go like, oh, okay, we don't have any arguments. So all of these things are not relevant at this point of time. From the callee perspective, um, the stack pointer always points to the return address at the entry point. And since we haven't really talked about parameters, yeah, you can just ignore this portion. And since we haven't really talked about local variables, you can also ignore this portion here. All right. And then you move on, look at the stack. You go like, okay, we haven't talked about arguments. This is all gone. We haven't really talked about local variables. This portion is all gone. It's all gone as well, at least for the time being. So now you also have to read this portion, okay? There's no need to preserve the values of registers A, B, or C. There's no assumption that the callee is supposed to do that. At the exit point of a callee, if it has a scalar return value, use register A for that. We haven't talked about that either. The callee is responsible to pop the return address. That's what we did today. The callee uses the popped return address to return to the caller. That's also what we did today. So this document as a whole is describing everything that you need to know about, how is the stack used, okay, as far as the caller and the callee are concerned. So we are just going to be we will add additional concepts, in the programs that will be working on based on this particular document. Um, so that's kind of the end of today's lecture. Do we have any questions? No questions? Okay. So if there are no questions, I am going to release today's lab, which is compiling C control structures. So let me uncheck it, check it first, and then show you the access code. I believe the access code is just GCC lowercase. Yep, it's GCC in lowercase. So when you do this homework assignment, you can choose to do it in a few different ways. For those of you who want to just kind of use your brain power to tackle every problem, you can do so, okay? And for those of you who want to go like, I'm gonna check out this code. I want to put this code into Logisim, inside the simulated processor and try to run it. You can do that too, okay? So you can use the assembler to help you. You can use the simulated processor to help you, or you can just look at the question and just try to mentally solve the problems. So those are all ways for you to kind of handle the questions for this one. Um, I think that's it. Okay, can you guys, can someone okay, you can get in. All right, very good. So I'm gonna stop the recorder and so I can upload.